Look at this graph. It's the graph of this rational function. If you'll recall that x equals 1 would be a whole because we could cancel a common factor of x minus 1 from the numerator and denominator. And what we'd be left with would look like a line, except the point on the graph where x is 1 is not defined, because obviously we could not put x equals 1 in this denominator. If you look at the limit as x approaches 1, that means graphically moving a point on the graph closer and closer to the point where x is 1, which is this whole. Notice that the function values are approaching 2 as my x values approach 1. The limit of the function is 2 as x approaches 1, even though x can never equal 1. But the limit as x approaches 1 is 2. So looking at this numerically, I'm going to make a table of values with x values approaching 1 from the left. In other words, they're smaller than 1 but approaching 1. And x values approaching 1 from the right. They're larger than 1. And let's look at what the y values do. So as x gets closer and closer from the left, the y values gain a decimal. So these y values are getting closer and closer to 2 from smaller values. And likewise, when I approach from the right, my y values are getting closer and closer to 2. So we can define this formally and introduce this notation. So if you suppose that some function f is defined near the number a, so thinking of this example, f of x was defined near the number x equals 1 for all values except 1, right? So that's what this sentence means. If we can make the values of f as close to 2 as we like, so in this case L is 2, by restricting x to be sufficiently close to a, in this case a is 1, then we say the limit as x approaches a of f of x equals L. So in our example, x is approaching 1, so we have a equals 1, and the y values are approaching 2, so L is 2. So a couple of things we need to know about limits. In this definition, this value of L has to be a finite number. So if a function's value is approaching infinity, that limit doesn't really exist. It has to be a finite number to say that the limit exists. And the limit has to exist whether I'm approaching the x values from the left or approaching x values from the right. The limits need to exist on both sides and equal the same value. So that's what this second item is saying. And remember, look, in the case of this whole, f of x doesn't even need to be defined at x equals a at all. So this was the concept of one-sided limits. I'm approaching from the right. My x values are getting closer to 1 from larger values, or approaching from the left. So that's the concept of one-sided limits. And that notation, you'll see the little superscript by the x value that's being approached, meaning from the right or from the left. And now for the limit to exist at x equals a, those one-sided limits have to be equal and exist themselves. So that's what this means. For the limit to exist, the limit from the right has to equal the limit from the left. So another way to say that, which you'll see in the text, is the limit as x approaches a of f of x equals L if and only if the one-sided limits are equal, and they also equal L. So if and only if means these two statements are equivalent. So if I can prove this, this is automatically true, and vice versa. So piecewise functions come up a lot because their graphs are good at illustrating weird situations with limits. So if you look at this piecewise graph, what's the limit as x approaches 2? Well, as x is approaching 2 from the left, the y values look to be approaching close to 3. As x values approach 2 from the right, the y values are approaching 2. So since the limit from the left does not equal the limit from the right, it does not exist. So the answer would be does not exist. Here's another example. There's a hole in this example at the point 1, 1. So what's the limit as x approaches 1? Well, since the limit as x approaches from the left, since the y values are seem to be approaching 1, the right are getting smaller and smaller and seem to be approaching 1. Since they both exist, those one-sided limits both exist and are equal to 1, then that limit for f of x approaching 1 must be 1. So now I've changed this function a little bit. I left that hole at 1, 1, and I've declared that the function value at 1 is 2. So again, my limit from the left is still equal to 1, and my limit from the right is still equal to 1, because only this hole is what's not equal to 1. So since the limit from the left equals the limit from the right, the limit for this is still 1. It's not 2.